Okay, the time is 12:30, so let's begin class here. Today we will continue with cluster analysis and most likely finish it. We're talking about that k-means clustering that we started last time. We'll talk a little bit more about project number 2 and likely do a little bit of the next section called discriminant analysis. So in terms of updates regarding Save Our Stats, the University of Nebraska Executive Graduate Council voted unanimously to retain each of the graduate programs corresponding to the departments that were slated to be cut. So that's another small good step in the right direction. On Wednesday, there was a UNL American Association of the University Professors press conference where they discussed that indeed that the financial health of UNL is much stronger than administrators have led on. There's a lot of press coverage regarding it. If you want to have links or if you want to see some of it, if you go to saveourstats.com, at the bottom of my timeline, you'll see the various news media sources that covered this press conference. Still no news about the APC report, the Academic Planning Committee, or the Chancellor's final proposal. Are there any questions before we begin here? Okay. So let's take a little bit of time to review k-means clustering. So k corresponds to the number of clusters that you have to decide upon before you actually implement this iterative algorithm. So you need to choose k. Maybe we choose, for example, 3. Next, you standardize your data in almost every situation. Again, they're similar to what we saw for hierarchical clustering. There can be times where it would make sense to not standardize your data, but typically you will always standardize your data. Next, you choose your initial cluster seeds. And all that means is that you choose, in this case, 3 observations from your data to be essentially the place where you start growing your clusters from. So corresponding to what we saw in the notes, here are 2 variables, standardized variables, Z1, Z2. We see all these observations plotted, and the stars are observations that we chose at random as the cluster seeds to grow the clusters from. Then the next step is that for all the other observations which were not cluster seeds, you measure the standardized Euclidean distance from those observations to each of the cluster seeds. And for whatever cluster seed a particular observation is closest to, that's the corresponding cluster that you put that observation in. So for example here, if I look at this particular observation, we can see that indeed that it is closest to that particular seed. And so we would categorize that into that particular cluster that would be formed. And you do that with every single observation. So you might end up with something that looks like this. Next, you find a new, let's say, center point to the cluster. And with k-means clustering, that means we use a mean for the center of the cluster. So in this particular case, for this kind of a purplish kind of cluster, the cluster mean relative to the Z1s and Z2s would be probably right about there. For the blue one, right about there. And for this last one, maybe right about there. Next, you do something similar to what we just did. For every observation, you measure the standardized Euclidean distance from that observation to this new cluster center. Do that for each cluster center, cluster mean. And then again, categorize those observations into the place or the cluster that has the smallest standardized Euclidean distance. After that, Then you might have to find new cluster means. And you keep on repeating this process of finding cluster means and putting these observations into clusters until you get to a point where the clusters aren't changing in terms of what observations are in it. That's k-means clustering. Any questions about that? Now, here's an alternative, more mathematical way to think about how this is essentially being done. I basically gave you an algorithm. Here's more of a mathematical way to think about this. What we are trying to do with k-means clustering is minimize this quantity, which is like a sum of squares that you've seen in other places when you've done like an analysis of variance, when you've done regression analysis. Let's dive into this equation some. So we have an x. Well, I could have wrote this in terms of standardized variables. I chose to be more general and say, well, we could just work with the x's too. But again, typically this will be with the z's, the standardized variables. Notice the first subscript here, r. We've used r in the past to represent the rth observation, where r is equal to 1 all the way up to capital N different observations. The second subscript then is an I, and we've used that in the past to represent which variable we're talking about. The first variable, the second variable, all the way up to, let's say, the pth variable, to be general. Now, the last subscript that is new to us, it's a little k. This represents which cluster you're talking about. So if I had, let's say, x sub 1, 2, 3, that would be the first observation, the second variable for that first observation, and then this particular observation happens to be in the third cluster. Okay? What we're going to do then within inside this parentheses is compare this, what ends up being a numerical value, to what's like the center of the cluster. So notice what subscript is missing there on this x bar part, the r. So what this means is that we're going to average over all observations that are within the cluster, find what that average value would be for that ith variable, kth cluster. So in other words, if I go back here, let's say we get to this point here. I'm simply, relative to z1, let's say, so that would be for the first variable, I is equal to 1. I'm just going to calculate this difference. And I'm going to put that within inside of parentheses. I'm going to do the same thing here, 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 and here for that particular cluster. Now, since you can see that some of these differences will be negative, some will be positive. So the way that we often get around that issue in statistics, we take a square. So we only deal with squared differences. And then what we do, we add up all these squared differences. We add them up over every variable that we have, every observation we have, every cluster that we have. And so what we're trying to do in a mathematical context is now trying to minimize this version of, you could say, squared errors, kind of. You know, ideally, we want to have clusters that might look something like this. Nice, compact, easily distinguished sets of observations. That's what we would like to have. If I were to calculate this, what's called the cluster sums of squares, for this plot right here, I would get something very small. Now, if I start having, let's say, clusters that look like this, well, now that's going to be larger. And eventually at some point, let's say maybe, so let's say we do have like a black cluster. When we start seeing these points kind of overlap, then this cluster sum of squares is going to get even larger. And in fact, it might start saying, okay, maybe some of these observations up here shouldn't actually be in this, let's say, this black cluster. They should be somewhere else. So, again, what we're trying to do essentially in a mathematical context is minimize this equation. Now, there's a problem here, though. Let me do some erasing. In order to try to minimize this equation, I described to you essentially an algorithm that tries to put the observations in all the clusters. This algorithm is not guaranteed to stop at the minimum possible value that this equation can take on. It can stop instead at what's called a local minimum. And just to make sure you understand what that means, and let's go back to your algebra days. Let's say I have f of x here, and I have x. So I just have some function of one variable. And maybe I have this function that, if I were to plot it, looks something like this. Okay? Now we can see with this function, the minimum occurs at this particular value of x. Let's call that x0 for the lack of a better way to denote it. It indeed, relative to that y-axis, has the smallest value. A local minimum, though, occurs right here. Okay? And so this algorithm that we have to do this k-means clustering could actually stop at a local minimum. Now, if you've had like a formal numerical analysis class, you talk about this kind of stuff a lot. This is essentially what could happen here. If you haven't had a numerical analysis class, that's fine. I hope, though, that it gives you the basic idea of you might not get to the point where you want to be. Any questions about that? Yeah.
Well, you were explaining this mathematical equation, and there are three summation signs: k is Gauss cluster, and all those. We need the summation sign when you say it's k is equal to 1, and then r is equal to 1. Why it is 1? And it should be r is equal to n, and then I is equal to p. Why we are defining 1 only?
Well, it's because
if we write 1, it means r is already first observation. And if we say I is equal to 1, then it means it's for the first variable.
So we have capital N different observations, okay? And so that means that R can range from 1 all the way up to N.
And that's why I said R is equal to N. Yeah.
Well, it could, let's write it out. Suppose, we will make this rather simple in terms of we have two observations, we have two variables, and we have two clusters, okay? So if I were to write this out, then I would have x111 minus x11 bar squared, okay? Next, I have x121 minus x21 bar squared plus, I'm going to erase this. Okay, plus x, let's see here, 211 minus x bar 11 squared. Do you want me to keep on going?
No.
Okay. Yeah, I mean, obviously, we have three subscripts there. It can be a little messy. And in fact, you could actually define these subscripts in a way so that the R is, let's say, within inside the kth cluster. And maybe that's what you were thinking about. The I could be within inside the K cluster as well. You could define notation like that. I did not. Any other questions? And I've kind of already answered this. This is some additional thing that when I was walking through my notes last night that I thought of. Do we want this value to be large or small? We want it to be small. Okay. Now, here's another problem with this algorithm that we have to try to find these clusters, or the members of the clusters. All this is dependent upon your initial cluster seeds. So if I come back here to the beginning, again, these cluster seeds are, you could say, are chosen at random. And the little stars there are the ones that were chosen. But instead, if I wanted to, maybe when I choose these at random, maybe I chose this one, and this one. Those three, all right next to each other. What can happen is that when you go through this algorithm, you might get a different set of clusters. So this algorithm is dependent on what you choose for the initial cluster seeds. You hope that you get to the same spot, but you are not guaranteed. So for that reason then, let me actually go back. I don't know why that is there. So for that reason then, you should rerun or run this algorithm multiple times to see if you get the same results, to see if you get let's say, a better set of clusters as measured by how large or how small that cluster sums of squares is. You'll see us do that with an example coming up. So a key thing is, you're worried about running into one of those local minimums. And for some reason, my formatting got a little bit off here. There's other small changes to how you can implement the algorithm that I described to you. I don't think it's worthwhile for us to get into all these small changes that can occur. I'll just mention one of them so you have a little bit of an idea of what I mean. So I'm going to do more erasing. So let's say I'm at this point of the k-means clustering algorithm, and I want to put this particular observation into a cluster. And so when I do that, I will find that indeed it should be the cluster that corresponds to this highest star there. Some ways to implement this algorithm for k-means clustering will say, okay, now let's immediately refine, or I didn't draw that very well, immediately change that cluster center for that seed. So it would be right there. And now let's go pick another observation. How about we pick this observation? Find the distance that observation is to all the cluster seeds or the centers. And once you do that, you'll find, okay, I'm going to now put these all together. Well, now I'm going to refine that cluster center and keep on doing that after every single observation. That's what some algorithms will do. And this is also just for your own benefit. I'm not going to ask a question about this on the test. There's other definitions of a center of a cluster, as you could imagine. We're doing k-means clustering. Well, guess what? There's k-medians clustering as well. You can explore that on your own if you want to. We'll just do k-means. Okay, so let's take a look at some actual data to do this. And we're going to work with this very small data set again because it's just a very good place to start. I'm going to turn off my spell check too. Okay. So here's a plot of the data, and I have the distances between every single observation. Now remember, one of the advantages of k-means clustering over the hierarchical clustering methods is that I don't need all these distances. I just chose this plot because this is a plot that we saw before. So how can I then tell R to do k-means clustering? Well, the first thing I need to do is I'm going to set a seed. We've looked at setting seeds before. The reason why I want to set a seed is because I want to be able to reproduce my results, my exact results. Because remember, k-means clustering needs to choose observations at random at the very beginning. So I'm going to set a seed, just pick a number randomly in your head. Then, to implement k-means clustering in R, I use the function called k-means. My data is in set 1. How many clusters do I want? In other words, what's k? I use the centers argument, and I say k is equal to 2. I put the results into an object called clus.toMeans, for the lack of a better name. And then I say at the command prompt, clus.toMeans, so I can see what happens. So now at the very end of this k-means clustering process, again, we would have two different clusters. Here's where the means, or here's where the centers are, which are means. Which observations are in each cluster? Well, observation 1, 2, 3, 4. 1 and 2 are in what's called cluster 2. This is cluster number 2. And 3 and 4 happen to be in cluster number 1. I have a plot down a little bit later in the notes. So what I did on this plot is actually put the cluster centers on there. So this was cluster number 2. This was cluster number 1. The green triangle represents the center of the cluster, which ends up being the mean for the two different observations. Okay. Oops. So next in the output, we see something called within cluster sums of squares by cluster. All this is that cluster sums of squares that we saw before, but now it actually says that this is for k equal 1. This is for, that should be a lowercase k. K is equal to 2. Okay? So if I were to add those two numbers together, I would get that cluster sum of squares. And just to show you that indeed that this is how it works out, in this little text box that I put together last night while I was going through this, I found that within cluster sums of squares for cluster number 1. So cluster number 1 again has this observation, which is at 4 and 2, has this observation, which is at 6 and 3. Here's 4 and 2, 6 and 3. I put in the corresponding cluster center. And I did the math. That was exactly what was in that equation that we saw before. And I get the 2.5 that was actually displayed in the output. This is just a nice little thing to do to verify that indeed you understand that equation, how it comes about, what's in the actual output. That's why I did it. There's some other stuff that's being displayed here that we'll talk about later. But then R tells you, okay, what's inside of what's actually being created for this object, this clus.to.means. And it actually lists out all the components of the list. I don't know why it does that. It does. All I would have needed to do instead was just type names, clus.toMeans, and I could see exactly what's saved in the list object. So if I wanted to explore what was actually in there, I could say clus.toMeans $cluster, and guess what? We get for each observation in the corresponding order, what is the cluster number? Now note that there's nothing magical about why why the first two observations are, let's say, called cluster 2, and the last two observations are called cluster 1 versus the opposite of 1 and 2. There's nothing magical about that for some reason. That's just the numbering scheme. So don't worry about that. Because naturally you might think, okay, well, observations 1 and 2, they should be in cluster 1. It doesn't matter. Just that they're in a cluster together. That's what matters. So what I can do now is take my original data that's in set 1 and then create a new variable in my data frame called cluster, where I put clus.toMeans $cluster. And now here's my data set with the corresponding cluster number as well. There's other ways I could have created this data frame, and one way is I show in this text box as well. Okay. Let's see here. So some comments at the bottom, page 61. Something that we've already talked about, what the cluster means are. I used the points function with the plot that was originally drawn to actually put the triangles on the plot for the cluster centers. Take a look at that on your own. I also go through the actual calculation in another way to find those cluster sums of squares. Again, take a look at this on your own. It's very similar to what I already introduced. Okay. So let's talk about in the output. About 3 minutes ago, I said, okay, we're going to talk about this additional thing a little bit later. So let's talk about that now. What this is trying to measure for you, it's a little bit like a coefficient of determination. It's just a measurement of how much variability is being captured within each cluster. I would not interpret it that way. Alone, just as it is, this is not worthwhile to interpret. We will interpret a very similar measure coming up that will allow us to make comparisons amongst different choices of K. But I at least want to explain to you a little bit about what's actually being displayed in the output. So you can see it's a ratio between two numbers, and we see the SS there. That means sums of squares. Now in a class where you learned about ANOVA, in a class when you learned about a regression, you'll probably remember learning about different kinds of sums of squares. Like a total sums of squares. Does that sound familiar? It's like the whole amount of variability possible that you could have. And that's what this tot SS component of clus.toMeans is measuring. All this is this quantity. In words, that means let's ignore the fact that we have K different clusters. And what we're going to do is we're going to average over all the observations and calculate the mean for a variable, for the ith variable, let's say. compare each observation's ith variable value to this mean, square it, add it up. That's all that this means. That's the total sums of squares. So total meaning, you're not even, again, paying attention to, you have clusters. So like, let's see, in ANOVA, when you have a total sums of squares, you're just ignoring any kind of factors that you have. And you have the total sums of squares. You're not looking to see how much variability that a particular factor is explaining about your experiment, your data. So if I look at the total sums of squares and I compare that to the total within sums of squares, this is the cluster sums of squares that we saw before. And let me just emphasize this. I'm not defining stuff precisely, but I don't think it's necessary. In other words, if I were to add these two things together, that's my cluster sums of squares. 5.78. So if I take 12.67 minus 5.78, I get something that's called the between sums of squares, which is 6.89. This is similar to in regression when you have the sums of squares for regression, how much variability that the regression model is actually explaining. It's like that measure. It's like the sums of squares for treatment in an ANOVA setting. Or sums of, yeah, that's a common name that people use. Okay? So that's what all these sums of squares are measuring. We're going to come back to sums of squares very shortly, and we're going to look at these sums of squares in more detail to help us make a decision about how many clusters we should choose. Okay? Now, as I said, this k-means clustering is dependent upon what you choose for your initial cluster seeds. So what if we choose, how about we choose a different seed number? So we set, let's say set.seed 7813 this time. Use exactly the same code, and guess what? We get different clusters. So here's the cluster means. Let's see, do I have a plot? No, I don't. The key is this. Here are my observation numbers. Observations 1 and 4 now are together in a cluster. Before it was 1 and 2, and 3 and 4. Now we have observations 1 and 4, and we have observations 2 and 3. So you can see again how it's dependent upon the fact that in this case different cluster seeds were chosen, and we end up with different clusters. Okay, now we get to determining the number of clusters. So I said before that a possible problem with k-means clustering is that you always have to say, okay, I want 5 clusters, or if I want 3 clusters. Where with hierarchical clustering, you didn't have to make that determination. So here's how to get around that potential problem. What we could do is calculate this measure here for, let's say, k equal 2, k equal 3, k equal 4, as high as you want to go for however many clusters you're interested in. Calculate this measure, and notice what this is. This is what I originally called the cluster sums of squares. I don't like the fact that I'm changing the name here. This is what excuse me, what people are referring to as the within sums of squares. And here in the in the denominator is the exact same name that I did use before, the total sums of squares. We're going to look at that ratio. The smaller, well, let me say this first. Remember when we introduced this numerator? We said we want this to be a small value. So we want this ratio to be a small value. The smaller, the better. But we have one problem. Sorry, we always have a problem. We have one problem, and that is the more clusters you have, the smaller this number will always get. It's kind of like, sorry to go back to this, R squared, the coefficient determination regression. All of you should know that the more variables you add to the model, the R squared is going to keep on going up and up and up. Even if the variables that you're adding are nonsense, it still will go up a little bit. Here, as we keep on adding more clusters, this ratio will get farther and farther and farther and farther and farther down. So what we end up doing is this. We do a plot where we have this ratio on the y-axis. We have values of k on the x-axis. And what we're doing is we're going to look to see where does adding more clusters basically not give us that much of a benefit. So in this particular case, we can see, oops, sorry, don't want to draw it there. Once I get to 4, it doesn't seem like I'm benefiting that much more if I go to 5, 6, 7, and so on. So because of that, then, 4 is probably the best. That's how you choose K. Any questions before we look at an actual numerical example about that? The key is you try a bunch of different possible values for K, you do a plot, and from that plot, you make a determination what the best value of K is. Now, let me also say it doesn't stop there, though. You know, with hierarchical clustering, we saw we could do plots of the principal component scores. We could do parallel coordinates plots. We could do a variety of different plots to try to make sense of the clusters that we see. You know, or I should say, do the clusters make sense? And so, even though this plot says 4, I'm still going to do some other kinds of plots, like the principal component scores, the parallel coordinates plots. I'm sorry, the scatter plot, the principal component scores. The parallel coordinates plots of the original variables or the principal component scores. I'm still going to do that and see if the clusters that I've chosen make sense. Okay? I guess that's what I have right there. Good. Now, as I said that, you know, if you use a different set of seeds, cluster seeds, you could get different clusters. And so you need to take that into account and try to redo your clustering method multiple times. And so there are 2 different approaches. Number 1, use a few different seed numbers, just like what we did in that previous example, prior to running, use a few different seed numbers with k-means. Compare the clusters that you found and look to see if, let's say, any of them are better. Now, how do you make that decision? What's better? You could look at this. You could look at a plot of the principal component scores and stuff like that. That's how you can make that decision. Here's something a little bit easier. There is an argument in k-means called n-start. And if I said n-start equal 10, k-means will automatically redo k-means clustering 10 different times for you. It will use 10 different randomly selected initial cluster seeds. What it will return to you as a result is not all 10 results. Rather, it will return to you the result that gives you the best W. So that's a little bit of a disadvantage. I might want to see, well, what were the other 9? It's not that big of a deal, but this is what can be done. So let's look at the goblet data now. So with the goblet data, again, there's a decision about, do you want to use the standardized variables or the original variables? Just to save time, I'm only going to do the standardized variables here. I use k-means clustering, where I start off with, I don't know why I even started off with k equal 1, but I did. Started with capital K equal to 1, I go all the way up to 10. So essentially k equal 1 is you just have one overall cluster. You have to start somewhere. Also, for each of these k's, I am going to use n start equal 10. So essentially what I'm doing here is k-means clustering 100 different times. Okay. So here's how we can do this. Since I want to go from capital K equal 1, capital K equal 2, all the way up to capital K equal 10, I can put this in a nice simple for loop. So I'm going to create an object called k.levels, for the lack of a better name, set it to be equal to 1:10, meaning 1, 2, 3, all the way up to 10. I need a place to save my results that I get from the W that's going to be actually outputted. I decided to call it WSS. This is within cluster sums of squares. I'm going to write a note to myself to be more consistent in the future. This again is just the original equation I showed you at the beginning of our class today. I'm going to set it equal to this. Does anyone know what's going to be inside, or what's going to be the result of using numeric length k.levels? It's a common thing that we do in R whenever we want to eventually save results.
Save as a number.
Excuse me?
Save it as a number instead of taking it as a factor.
It's going to allow me to save it as a number, yes. Exactly. So yeah, we want to save the number. But what I'm going to actually do here, what length k.levels does, it says, well, how many values of k do I have? 10. It's the length of this vector that we just formed at k.levels. And what the numeric function does, it's kind of like it just creates a dummy vector of a particular length, 10 in this case. And let me just emphasize, when you encounter code that's unfamiliar to you, especially code where you have functions embedded inside of functions, what you can do is maybe just execute part of the code to see what happens. So let's do k.levels. Oops. I don't know what happened there, because I was not running that. Let's see here. Okay, so k.levels. Make this a little bit higher. There we go. Then, what does the length function do with k.levels? Let's run that. It tells me what the length of that vector is. Then if I run it with numeric, now I've basically initialized a vector with zeros. And this eventually is going to be a place where I'm going to store all my results from using k equal 1, 2, 3, 4, and so on. So let's go ahead and do that. So I'm going to set a seed so I can reproduce my results. And I'm going to say, for capital K in my k levels, do the following. First part should be familiar. K means x equal my standardized variables. Centers equals k. So the first time through this loop, k is going to be 1. The second time, k is going to be 2. I want to repeat this 10 times for every single k. I'm going to save the results in an object called clus.means. Next, I'm going to take out the within sums of squares from clus.means, sum up those within sums of squares. So if I have, again, 2 clusters, I'm going to get 2 different sums of squares out. I sum them, and then I'm going to put them in to the kth element of my save.wss. So let's actually run this just to show you. Suppose k is equal to 2. There's clus.means. Notice how I have 2 different clusters. Notice the corresponding cluster means. If I look at clus.means $ within SS, there's those 2 sums of squares. Then, if I look at save.wss, the kth element, there we have it. It's just the sum of these 2 numbers. If I look at the whole vector, now, I don't think I initially do this again. There. We see how it was inserted into the second element. Now, if I run this whole code for all values of k and say save.wss, there's all of them. Excuse me. Now, so after I do that, the very last clus.means that I have, I'm going to extract out tot.ss, the total sums of squares. I'm going to put that in an object called TSS, for the lack of a name, total sums of squares. Now, why can I only look at the very last thing that was just formed with k equal 10 and not worry about k equal 9, 8, 7, or 6 to find this value? Perhaps it's a trick question. Is my total sums of squares going to change depending upon k? No. Because remember, that doesn't care about how many clusters you have. So that's why I can do that. So then I form a data frame where actually this is actually incorrect there. Let me redo that. That was disappointing. Then I form a data frame where I put k.levels, and then I take that ratio that we're interested in, that W, and this is what I get. So for each of the possible values of k, I see that W. Next, let's plot it. So on my x-axis, I put my different k's. My y-axis, I put the corresponding W. I put some nice titles on the label for the x-axis, y-axis, and so on. And this is what I get. So again, what we're looking for here is, when are we not getting much of a benefit anymore by increasing k? And so we can see definitely when we go from 1 to 2, yeah, that's a huge benefit. 2 to 3, sure. 3 to 4, yes. But we keep on getting smaller. 4 to 5, okay. 5 to 6. I mean, definitely down here, it doesn't look like there's much of a benefit. We're at least getting a benefit up to that point. So the question is where do we stop? As I say here, maybe 5. And based upon how I'm phrasing this, you might expect, okay, there's probably going to be more than one correct answer. Choosing 8 and 9 clusters is not right. Choosing just 2 clusters is not right. But 4, 5, I don't know, maybe 6. I think more 4 or 5. But you can see again, somebody might have a different answer. So next, how about we examine what it looks like to have 5 clusters? So what I can do is set a seed again, use k-means, and notice what I'm doing here. Centers equal 5. I am going to do k-means clustering 10 different times and try to find the best of those 10. Note, the W that I get here could be different than the W that I got from that for loop. You would hope it's going to be very similar because you were using 10 different k-means clustering for that k equal 5 before. You would hope it would be very, very similar. It should be. But again, you could get something a little bit different. Okay, so now we look at cluster.5 means. So we have 5 clusters. Those are the corresponding final means for each of the clusters for each of the variables. So this means, for example, observation 1 is going to be in cluster 4. Observation 2 is going to be in cluster 2, and so on. If I were to add up all these within cluster sums of squares, this would be then that cluster sums of square thing measure that I originally gave you. Next, we want to do some visualization to see if these clusters make sense. Similar to what I did for hierarchical clustering, remember I put together a function to help you out that does principal component analysis and does a whole bunch of plots of the scores. I've created one of these functions now with the k-means clustering results. You are responsible to go take a look at that function and understand how it is implemented. It's going to be very similar to hierarchical means. Let's focus here in class, though, on what we get as a result. Again, we've got 5 clusters. So here's one cluster, here's one cluster, here's another cluster, and here we go. Those are the 5 clusters. Obviously, some of them make sense. The 4, 5, 17. It was kind of interesting that 18 was put with 3 and 16. But why? Well, take a look at the plot on the right side. Once we incorporate then that third principal component. Look at how the size of those bubbles are similar for 3, 16, and 18 in comparison to what we had for 4, 5, and 17. That's why 18 was put with 3 and 16, that third principal component. And just also for emphasis here, that plot on that right side, the actual observation numbers are essentially where that principal component score would be, and I colorized the observation number by the corresponding cluster. And we can also look at some 3-dimensional plots too. It is interesting. I think we looked at this before too. We have this, to use a non-statistical term, this big gob of points in the lower left-hand side. And it's interesting how this k-means cluster ended up breaking them up. And what we've seen before when we looked at stuff with a three-dimensional scatter plot is that indeed some of these points are a little bit below that green plane. You can actually see it here. Some of those points are below that green plane. Those correspond to a particular cluster. And then some points are above and a few that are just below as well. That correspond, and then those were all kind of put together. You can run this code yourself. Look at the 3D plot and spin it around to see this again too if that's not familiar or if you don't remember that from last time. So in the end, I'm a little concerned that there maybe are too many clusters here. I don't know, maybe it's just my bias. I've looked at this data set for a number of years. That big gob of points in that lower left side, I kind of like them all together to be in one cluster. Here's an interesting question for you. So I just showed you some principal components score plots. How could I plot now the corresponding cluster means in terms of the principal components? So in other words, I like to be able to redo this plot that's in the maybe upper left-hand side here and put like a plus here, maybe a plus there, and so on, corresponding to where that cluster mean would be. How could I do that? Can it be done? Yes, it can be. That's what I'm asking. Okay. So, we talked about when we did principal component analysis, let's say I have a new observation. Let's say a new goblet. How could I find its principal component score? If we think of it just in terms of R, remember there is a predict function. And I could say object equal, whatever that PCA result, whatever object I store that result in from printcom, comma, then there's another argument that's very important here. Anyone remember what that is? It would be a similar argument that you would use with regression models. And you want to predict the y, you want to get the y hat, let's say, for a new observation. New data, yep. So if I wanted to get for a new goblet what the principal component score would be, now if I'm just thinking in terms of R, I could create a data frame, put that new observation, those new measurements of the goblet, into a data frame, use the new data argument, and I get the principal component score out. Of course, if we think of this outside of, let's say, R itself, what I want to get is essentially a y star. And I have an actual equation that I can use to get the y star from my new observation. So now if I want to plot the cluster means, what goes in new data? The cluster means. So let's say your first cluster, we saw how we can see what the means are, put that into a data frame. The data frame goes into new data. Use the predict function with it. Then what will be a function R that you could use to plot the point? The points function. Okay? So take the principal component score for the first principal component, for the second principal component, put that into the points function, and you can plot the mean. Okay. Now you could also do parallel coordinates plots here to try to make sense of what we see. And so that's what I'm doing here. For my color, I'm going to use exactly the same color as what we saw with the principal component score plots. And this is what we get. Let me make this a little bit smaller. So just to relate it to the principal component score plots. So for example, the black cluster was 4, 5, and 17. Let's see now. 4, 5, 17. Yeah, that makes sense for them to be in a separate cluster. And remember, in the principal component score plots, that lower left-hand blob, which was blue and red. Look at the blue and the red here. They are really kind of overlapping. And so that's where that maybe questionable cluster is. I mean, we do see some differences, though, from looking at this. And so what I also have here then is some information to try to interpret the clusters that have resulted. So for example, the black ones, these all have large values for all variables. Green, large values for W1 and W2, but smaller values for W4, W5, and W6. What that corresponds to is variables 1 and 2 were the top of the goblet, variables 4, 5, and 6 were the bottom of the goblet. And so you can keep on going farther and farther and farther with your interpretation as I do here. Okay? Let's see. Let's look at 3 clusters now. So let me go ahead and draw this. There we go. This is a little bit different from what I think we've seen in the past with hierarchical clustering. I mean, it makes some sense. The thing is, we get some observations that it's not necessarily clear should they be in one or the other. Perhaps this is a thing that, let's say, an archaeologist. Let's say it's a statistician working with archaeologists. The statistician presents these plots to the archaeologist. And the archaeologist will say, yeah, that makes sense, or I don't know about that. And then based upon that interaction, then you can make a decision about what will be best. Because just alone here, again, you can see that there's not necessarily one correct answer. Yeah. Any questions? Let's take a look again at the project. So problem number 2 on the project is dealing with k-means clustering. So you're using exactly the same data as you would do with 1. And you're going to repeat a lot of the stuff that we just did. So you're going to need to use k equal 1 to 10, set a particular seed number before you do all that so that everyone will get the exact same result. Use the k-means clustering in a for loop, and use n start equal 10. Based upon what you see, tell me why 3 or 4 clusters may be appropriate. Now, Not saying that both are appropriate. I will tell you that one is better than the other. But I want you to go through the reasoning similar to what we did here. Do a plot of the W versus the K. Tell me why someone could pick 3 or 4 from that plot. Then, for both 3 and 4, I want you to rerun k-means with n star equal 10 with this particular seed so that everyone gets exactly the same result. Rerun k-means, show me the output. Next, for 3 and 4 clusters, construct parallel coordinate plots with cluster memberships appropriately identified. Interpret the clusters. Similar to what we just did. Based upon the parallel coordinates plots, which is more appropriate for a number of clusters, 3 or 4? Now note that we are not doing principal component scores here. Why? I'm just trying to save you time. It will be good practice for you to run my function with the principal component scores and make sure that you can go through the formal interpretation that way. Because just because I don't put it on the project doesn't mean I won't put it on the test. Okay? Then lastly, remember we talked about last time how doing cluster analysis on this data set probably wouldn't be done in practice because we have natural categorizations already for each observation. It's the position. So now this is where this can all become like a little bit of a teaching tool. So what I want you to do is run k-means clustering with k equals 7, C number of 6767. Let's compare the results from that to the positions that we know. Now, the ideal thing would be is that the clustering methods will put everyone that's an offensive lineman in the exact same cluster. Puts everyone that's a quarterback in the exact same cluster. Ideally, this is what we want to have happen. Let's see if it happens. So in the end, what I want you to do is construct a contingency table. Let's say that we have the actual position of the player here. We have the cluster number here. I'm not getting the order correct here, okay? So we have like offensive lineman, which I'll just call OL, quarterback QB. Sorry, I don't remember off the top of my head. That's the exact abbreviation in the data set. We have the cluster number as the columns. And I want to know how many fit in that categorization, how many fit in that categorization, and so on. Based upon that, you will be able to make a determination, is this clustering method working as good as we would like it to be? Or maybe for some positions it works, maybe for other positions it doesn't. And if you want to go a little bit farther, you could use, if you have football knowledge, you could use your football knowledge to explain why maybe the clustering method is not working sometimes, but it is working other times. Now, how can you construct a contingency table like this in R? There's a variety of different ways. Here's one particular function that can be very useful. It's called xtabs. If you've ever heard of cross tabulations, crosstabs, that's essentially where this function gets its name from. And you can use for the first argument formula equal, and imagine you have a data set, and I just happen to call the data set actual.cluster. Your data set that you choose to call it could be something else. And this is like in my answer key. And I have a variable in that gives me the actual position of every player. And also I have a variable in it that gives me the actual cluster classification for every single player. By using code in this kind of a syntax, I will get a contingency table like this. Now, that is not a 100% perfect explanation so that you can go out and completely use this function. But I've given you a tool here to help you learn how to use a function yourself. Look at the help for XTabs. Or if you know of another function that will do this, for example, the table function will do this too. Do note also, I forget what the correct ordering is here in terms of these two variables, in terms of which goes on the rows, which goes on the columns. I could have actually reversed it by accident. It doesn't matter. The key is create a contingency table that summarizes these results. Are there any questions? Okay, so we are running out of time here. I don't think it's worthwhile to start then the next section. So let's talk about then what's next in our course. I'll have office hours after class, and I will actually be in this classroom for the office hours. Okay? On Tuesday, we will start discriminant analysis. We'll look at project number 2 some more, because that last problem in the project is dealing with discriminant analysis. Looking further ahead, project number 2 is still tentatively due for Thursday, November 13th at 5 p.m. Test number 3 is Thursday, December 4th. Are there any questions? Okay, that's all for today then.